Now it's on. All right. Okay. I want to thank the organizers for inviting me and getting me here finally. Last time I didn't make it through all my own fault, not realizing my passport was full. But I'm here now. I want to talk to you about the next steps for robotic exploration of the moon. And I'm going to talk about three things: sample return, exploring for resources to sustain humanity on the lunar surface, and also commercial enterprise, and then geophysics, something that I have really gotten into in the last couple of decades, especially on the moon, because we know so little about the interior of the moon. But I'm going to start with samples because they are the gift that keeps on giving. And I put this slide up to give you an idea of what that means. After Apollo was concluded and the preliminary examination of the samples had been done and published, the moon was considered to be very, very dry. However, in 2008, when the analytical technology had advanced to actually make these very detailed traverses through some of these glass beads that are about 1 millimeter or less in diameter, you can see there's diffusion profiles of different volatile species out of those glass beads when they were erupted to the lunar surface. And this demonstrated that the moon, the lunar mantle, actually did contain reservoirs of volatiles in some quite considerable amounts, and that we needed to rethink what we thought about the moon being dry and having a dry interior. So sample return is the way to explore this now that we have a lot of global data sets. And I just put this up here as a give you an idea of the different types of documentation from the national academies and the lunar community that points to sample return. So this is something that we need to think about, because the United States has never returned successfully a sample from a planetary surface robotically. OSIRIS-REx is on its way back, but it has not landed yet. It's never done it at the moon because they sent humans. Soviet Union has done it. China has done it from the moon. But with these global data sets, we can now construct these landing sites for different lithologies to answer different questions. Now, I don't expect you to take all this in, but there are many places on the lunar surface that are scientifically interesting, because we either know nothing about it, or the samples that we have asked questions that we need samples from other locations to answer. The other thing that we have, that we now know from orbit, that there are lithologies and rock types present on the surface that we don't have in the sample collection. And overall, if we put that in the sort of the unifying model of the moon, that it had a very violent beginning from an impact into Earth, the material thrown up for that further coalesced to form the moon that initially underwent differentiation by a magma ocean. Then we can start to pinpoint these samples and start to say we can explore this phase of lunar evolution. The other thing that you see at the poles, and you can see at the top, the North Pole and the South Pole, there's now evidence for hydrogen deposits or water ice in some of the permanently shadowed craters at those polar regions, and we'll come back to that in a little bit. But robotic sample return, what does that mean? What technology do we need to do it? So we need precision landing. If we're going to have a static lander, we need to land on top of the sample we want to collect. Is bulk regolith sufficient to answer the science question? Will hand samples be necessary? Bigger samples that will require different sampling techniques and different sampling mechanisms. Would a fetch rover be required to go out and do reconnaissance around the landing area and do the sampling And then how far would that need to move and traverse in order to complete the science goals? How will the samples be transferred to the return vehicle? Will samples require special storage conditions? For example, if we're going to sample some of these ices at the poles, we would need cryogenic sampling and storage and then curation back here on Earth. And are surface samples sufficient, or will drilling and coring be needed? There's a question earlier on today about drilling on the moon and Mars. And the deepest drill was 3 meters so far, and that was from deployment of the Apollo heat flow experiment, deployed at 3 locations, Apollo 15, 16, and 17. Unfortunately, Young at Apollo 16, once the heat flow probes were deployed, tripped over the power line and ripped it out, and it never actually returned any data. But we'll forgive him for that. So reconnaissance sample return is what the robotic return would actually encompass. Because one sample will not answer all the questions, but it's going to be a start. With the United States space policy actually directing NASA to establish a permanent human presence on the moon, we need to find those areas where sending humans would be important to understand these science and exploration questions. So this reconnaissance sample return becomes very important. Evolving to more targeted samples requiring fetch rovers and precision landing is something that we can look at in detail now. We have photography of landing sites at sub-meter resolution, and we can highlight the locations for human exploration. With mobility over several kilometers, we could then undertake mapping and detailed sampling of an area to bring back to one locations, maybe for humans to then return. Mapping lunar magnetic swirls, something that's very enigmatic on the lunar surface, but we really don't know anything about it. We're understanding the extent of pyroclastic deposits which contain volatiles, understanding how deep they are, how extensive they are, and how variable they are in composition. And then local regional subsurface regolith stratigraphy is important for looking at potential mining sites and the ease of manipulation of regolith. And the one at the bottom is going to segue into the next one, and that's resource prospecting. We know that the moon contains resources, but we need to find out more about it. So talking about the lunar resources, there are 3 broad categories of potential resources that will enable humans to live off the land once they get there. We've got polar volatile deposits in those permanently shadowed craters at the poles. We've got regolith. It's important for building materials, extraction of metals and oxygen. Solar wind volatiles are implanted there, including helium-3, and then platinum group metals from meteoroid bombardment. If you look at the diagram over here on the right-hand side, the top right, that purpley color represents oxygen, which is about 40 to 45%, no matter what type of regolith you're looking at, whether it be highlands, high titanium Mari, or low titanium Mari. They all contain about the same amount of oxygen. Again, something that's important if you're trying to get oxygen for life support. You can get that through electrolysis anywhere on the surface of the moon. The other thing I point out is that in this prosolarum creep terrain, the PKT, which is enriched in, it's defined by thorium abundance, but it's enriched in rare earth elements. This is something that we need to think about because of, I was talking to Fumio at lunch about rare earths and the need for rare earths in the economy. Is there enough there that would be considered an export back to Earth, depending upon the market price? There's thorium and uranium enrichments in that area as well, with regard to fission power that is going to be required for reliable power sources off Earth. And then we get to these pyroclastic or these volcanic glass deposits. some of which have been shown from orbit. I don't know whether you can see it in this particular diagram, where we get the reddy colors get up to over 300 part per million water in some of these regional pyroclastic deposits. That's very intriguing that depending upon how extensive it is, whether or not these volatiles are viable for use in terms of life support or even producing rocket fuel. But what we do know is that these types of deposits will contain important metals such as titanium and iron for construction. So these represent the lunar resources in the sort of categories of lunar resources, and we're going to focus in on these polar volatile deposits because these have been designated the low-hanging fruit, the ones that we need to go after to get water to now allow humans to live and work productively off Earth, on the moon, sustainably. And there's that sustainable word again. So, importance of lunar resources, it can potentially enable sustainable human exploration, i.e. it can facilitate a permanent human presence on the lunar surface. It can also potentially facilitate commercial involvement in lunar exploration. And as a university professor, that means jobs for my graduates when they go out, and I can ask them, what are you going to do when you graduate? And they say, well, I'm going to go work on the moon. Maybe it's not science fiction. And it can also promote international collaboration and cooperation because space is expensive, and international collaboration and cooperation will allow diplomacy to occur in an era where diplomacy is desperately needed. But the reason I bring this up about resources is the term resource has been used by several space agencies and governments when they actually mean reserve. And it's a very important distinction here, the difference between resource and reserves. So if we look at the diagram on the right, you can see that we've got resources proven and unproven, and then we've got reserves, and they're a subset of resources. And you can see here, just to read the definition, resource, a concentration of naturally occurring solid, liquid, or gaseous materials in or on the crust in such form that economic extraction of a commodity is regarded as feasible. Now, a reserve is where we've got a lot more data about that resource, and we can say that this is now identified, from which a usable mineral or energy commodity can be economically and legally extracted at the time of determination. And this is a very subtle difference, because we're talking about economics, making a profit, bringing the commercial sector in, but also legally. Is it illegal to mine on the moon? And technically right now, if the United States was to go do it, that would be illegal. And I'll get onto that in a little bit. So I want to put this up about the in situ resource utilization value chain. And you can see here, we've got a little diagram on the right, and we've got a couple of roadblocks in that value chain. And that's demand, or the market, and the reserves. There is no market or demand for resources, lunar resources, right now. So there is no economic value placed on what is there. We don't know if there are any reserves on the moon. Now remember, a reserve has an economic connotation to it, so that economic that value cannot be placed on it because there is no market. So we have to solve that if we are actually to actually move forward with using the resources on the moon to sustain humanity on the moon. So ground truth data and demand need to be attained, and they need to be established if lunar resources are to be looked at in terms of being reserves, and are they reserves? So what we've been pushing quite hard in the last 12 months is this international lunar resource prospecting campaign, focusing initially on the water ice deposits at the poles of the moon. And what you see here is a paper that came out last year, Holly Brown's work, using 10 orbital data sets to show the top 10 targets over here in this diagram here, top 10 permanently shadowed craters for the most likely to contain usable quantities of water ice. But when you look at the area of those top 10, it's over 6,000 square kilometers. So no one nation is going to do a prospecting campaign just for the top 10 permanently shadowed craters, let alone looking at the other resources that are there. So legally, we have to look at the Outer Space Treaty with regards to the legality of space resources. Exploration and investigation of the moon should facilitate, promote, and encourage international cooperation. It says, outer space, including the moon, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. And then it says that the exploration of outer space, including the moon, shall be carried out for the benefit and in the interests of all countries, irrespective of their degree of economic or scientific development. So an international lunar resource prospecting campaign is now compliant with the Outer Space Treaty, because it is no one nation is going forward to colonize the moon. We go forward together. And the types of data that would be needed are from surface mobile assets. And there's a lot of technology that needs to be developed there, because we need to look into the third dimension. We need to look below the surface, not only with ground penetrating radar or neutron spectrometers, gamma ray spectrometers, but with drills. We have to drill into the surface of the moon to understand at least the top meter or two of regolith to see how variable the different deposits are. So finally, the last part of the talk is this Lunar Geophysical Network, which is, again, a robotic mission to the moon to deploy 4 geophysical nodes. In the last 2 decadal surveys, the new one is Origins, Worlds, and Life. It covers the period 2023 to 2032, and it lays out the scientific objectives for the Lunar Geophysical Network, as shown over there on the right, looking at internal structure and composition, looking at variability of that structure and composition, looking at present-day lunar seismic activity and the heat flow budget, so we can understand the distribution of heat-producing elements throughout the moon. We look at Apollo knowledge. We did have a geophysical network on the moon during Apollo, and you can see the diagram over there on the right, little map. The green triangle is the passive seismic experiment, because these were all deployed during the Apollo lunar surface experiment package, the LSEP. And you can see here the heat flow experiment, the lunar ranging retroreflector, the lunar surface magnetometer, and the passive seismic experiment all form part of a geophysical network of varying degrees. You see the laser ranging network also has 2 Soviet Lunokhod rovers on there, because they at Lunar 17 and 21, because they had retroreflectors on them as well, and they're still being ranged to. And in fact, 17 was lost for many years until 2010, when Lunar Reconnaissance Orbiter actually found that rover, and it was the coordinates given for its last position were incorrect, and that has now been added back to the current network. And laser ranging is the only ongoing Apollo experiment that still happens today. So a little bit more about Apollo knowledge. We got 4 types of seismic events that occur on the moon. We've got deep moonquakes that occur in nests of a very unique seismic signal. And they're small magnitude, but these nests allow us then to get an idea of where it's located and also its association with tidal forces, because these nests are active, more active certain times of the month as the moon goes around the Earth. Thermal moonquakes are the smallest, and this is where we go from night to day and day to night because of the about 300°C temperature change. Meteoroid impacts, a lot of meteoroid impacts of various sizes. Usually, most of these are small. So what this tells us that any surface habitat we have on the moon has to be buried, not only to protect from meteoroid impacts, but also from radiation. And this, the enigmatic one, shallow moonquakes. And these are the largest of the moonquakes that were defined by Apollo. At least one per year over the life of the Apollo network was magnitude 5 or greater. And they have relatively shallow focal depths. They are now considered to be associated with thrust faults that we have been photographed on the surface of the moon, but that's still being investigated. And I put this diagram up here about body wave magnitude against cumulative number of events. And you can see this is the central seismicity of the United States is the solid line here on the left, and the dots represent the recorded shallow moonquakes by the Apollo Passive Seismic Network. And then you've got some lunar seismograms over there. And if you look at a shallow moonquake, these little graduations here are in 10-minute intervals, and you can see maximum ground motion occurs for about 8 to 10 minutes. It occurs much longer than on this planet because the moon has a much higher seismic Q. It doesn't have any clay minerals or any hydrous minerals to deaden that energy. So the network was located on the central near side, so its depth resolution was very poor. It couldn't give us unique solutions to the deep interior, and especially looking at the core. The far side we know has thicker crust, but we have no seismic data from the far side as yet, and we see that as offset center of mass, center of figure. We have a much thicker, low-density feldspathic crust on the far side than we do on the near side. Hence, we have all the Mare basalt eruptions, or pretty much all the Mare basalt eruptions on the near side. So why is another lunar geophysical network needed? Well, we don't know the extent or duration of how the extinct lunar dynamo was actually started, or if it actually existed for considerable periods of time. We don't know the exact origin of the magnetic anomalies on the lunar surface. Here's one of these lunar swirls in the bottom left here from Rhina Gamma. We don't have ambiguous observations of the structure of the mantle. We don't know anything about a partial melt layer above the inner core. We don't know how surface hemispherical observations propagate into the interior. How does that crustal dichotomy go into the mantle? And we don't understand why or how all moonquakes occur. So we have a lot of things to still answer, with a lot of intriguing questions that have come from past 50 years plus now of analysis of lunar data. The other thing that got my interest in doing some work on some of those volcanic glasses, what we see here is that some of these glasses plot in regions where we would expect garnet to be in the mantle source. And you can see that in both of these diagrams. And it's been retained after partial melting. So that means they come from depths of greater than about 500 kilometers. Now, if that's the case, well, I said, well, we can look at the lunar seismic data to actually answer that question. But they cannot give us an unequivocal answer. It is ambiguous in how they can determine or give us an answer. So it could be magnesium-rich olivine, but the geochemical data, at least in some of these glasses, suggests that garnet is present. The final thing is why we need one is to evaluate the seismic hazard to any lunar base that goes up there. Now, Yoshio Nakamura, back in 1974, published this paper of where the shallow moonquakes were occurring. And this is his best estimate on the basis of the fact none of them occurred within the network of the Apollo seismometers. But you will notice that one of those is down in the South Polar region, which is where China, Russia, United States want to put research bases or base camps. And this probably needs to be reconsidered in terms of why they want to put it there. The other reason I would like to have another network is to look at the potential for LLSVPs on the moon. There's an idea of having the LLSVPs being long-lived remnants of a magma ocean cumulate overturn event, some of those sinking to the bottom, and the moon has basically preserved that. It has not evolved much past the magma ocean event and seismic and the cumulate overturn. So it will be intriguing to see whether or not we can get the data to understand whether or not LLSVPs, fossilized LLSVPs, actually exist at the lunar core. So the planetary, we had a planetary mission concept study funded in 2019. That's available on the web, and globally distributed network of seismometers, heat flow probes, electromagnetic sounders, and laser retroreflectors would be enabled by this particular mission. And the baseline mission, 4 identical landers. You can see here the stretched out moon there. We've got 3 on the near side and 1 on the far side that would be on the thickest portion of crust that we know. I don't have time to go into the justification for each of those. The threshold mission, we'd be able to achieve all our science objectives by 1 and 2 here on the near side in the near Aristarchus, number 1, and in Chicard Basin, number 2. And again, we would have to have a communication satellite to go and get the data back from the far side, but commercial entities are putting up those networks starting this year, so we're fortunate to have that going on. So development as of 10th of January. This is for the NASA's New Frontiers program, and the New Frontiers draft announcement of opportunity was released on the 10th of January. Lunar Geophysical Network is in there. We would have to get our proposal in by April 2024, and a launch during 2031 is the target date for that. So, summary and conclusion, sample return. Technology has been developed by JAXA for Hayabusa. And we've got opportunities for scientific and technology collaborations between JAXA and NASA or Japan and the United States. Development of reliable fetch rover and sample transfer and return mechanisms is also, it needs to be conducted, and this could be done in a spirit of cooperation in order to be mutually beneficial. And then this is going to be very useful for establishing strong scientific collaborations if we do it that way, because the sample that comes back, portion goes to those countries that have been involved and to the scientists that work on such samples therein. And then resource prospecting is going to promote international scientific and technology cooperation and collaboration. And no one country can do this on its own. We need technology to work in these permanently shadowed craters with temperatures of about 40 Kelvin, pretty much constant year-round. So this is why maybe the water ice in these craters is not that economic, because there's quite some considerable challenge to getting the water out. The data returned, and you can see this little Venn diagram on the right, serves a number of different stakeholders from science, commerce, and exploration, but the majority of data that would come back from such a prospecting campaign would benefit all or multiple stakeholders. And this can establish strong commercial involvement and job growth if resources can be shown to be reserves. Again, for the Lunar Geophysical Network, an international team has been assembled, and we've also got commercial and government participation through 2 commercial companies providing landers and 2 NASA centers also being involved. In the last 20 years, new instruments have been developed. Heat flow probe, seismometer, laser retroreflector, and electromagnetic sounder. New batteries and landers have been developed. And establishment of this network is going to be critical for the safety of humans on the lunar surface. That's my talk. Thank you very much.